everybody, Doc here again. We've finally reached day 2, Calculus 1. This is lesson 4. Section 1-4, if you have the correct book. If you have this book, sorry mine's front's a little dirty, but if you have this book with the blue integral on the front, then it's in section 2-1. Now I don't know if the exercises are exactly the same. Like some of you, I'm still waiting for my correct book to get here. They actually sent me a message that they lost it in the mail. Can you believe that? Anyway, so moving on. We got lots to do. We're the tangent and velocity problems. This is when we're going to start introducing ourselves to limits. And I'm actually going to go to the book for a lot of this because they have some really good illustrations. So we're looking at the tangent problem. So here I have a circle and I have a tangent point. Well, how do I find slope at that point? That's the underlying question we're going to take a look at in this section, is how do I find slope at that particular point? So here's just an example of what a tangent line looks like. It contains one point up to the object or curve that we're talking about. Here's another example. Now this, people would say, is that a tangent line? No, it's not a tangent line because it goes right through the curve. But this does intersect C at a later interval, and that's okay because we're really concentrating on this point right here. So this is still a tangent line, even though later on down the road, it does in fact intersect the line. Now we're going to look at example 1. I want to find the equation of a tangent line, but we have to know its slope first to do that. We have a parabola. That parabola is x squared. We're curious about the slope at the point 1, 1. So let's think about what we know. We want to find the slope. And remember, your slope formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Now we only have one point, so we'll call it x1, y1, and that's what goes in here. So this value is whatever our function is, which in this case is x squared. And the bottom is our x. Here we have a nice illustration of what we're talking about. Here's the point in question. And the red line is the line that is the tangent line. Now, how do we figure out what the slope is? Well, we can start estimating. We could say, well, what if we get another point that's kind of close to that point, and then use those coordinates in the formula to guess what the slope is. So that's exactly how this started. So here they say, why don't we try 1.5 and 2.25? Now they got the 2.25 again by putting it into the equation x squared. So now that they have 2 points, they have the 1, 1 and the 1.5 and the 2.25, they can plug it into the slope formula and get a slope of 2.5. Now that is the slope of the line that contains those 2 points. So it's not quite the slope of the line of the tangent line, but it gives us an estimate of where we're headed. Okay? So if we try several values like that, here's a table that shows values that are close. Let's say we're going to get close to 1. So we always say we're going to come from the positive side or come from the negative side to 1, or come from the left or come from the right. So what I mean by that is, if I have a number line and I have the number 1, which is the number in question right here, I'm going to come this way and come this way. So I'm going to come from the left and come from the right. If I come from the left, then 0 is over here. So I'm going to have all these numbers between 0 and 1. That's the second table. So if I use these points and plug it into what I just did up here, these are the values that I will get. If I also test it from the right, so I'm going to start at 2 and come close to 1, then these are the values I'm going to get. So why are we doing that? Well, we want to take a look at if they're both getting close to a specific number. From the left, looks like we're at 1.999. Pretty close to 2. From the right, we're at 2.001. Again, pretty close to 2. So we can summarize and say that since they are both approaching 2 from the right and from the left, then our limit of this function is going to be 2. Again, our limit of x squared minus 1, x minus 1, as we approach 1, this means as we approach 1, is 2. So this tells us where we're concentrating on, and this tells us what we're getting close to. Now, we're going to go ahead and assume that that is indeed the slope. It looks like it's going to approach that. Looks like we're pretty close. We have a continuous parabola. We don't see any breaks in there, so it looks like we can probably say that that slope is 2. So now if we want the equation of the tangent line, we just have to put in our point slope formula. Remember, our point slope formula is y minus y sub 1 equals the slope times x minus x sub 1. Okay, so that's our point slope formula. Our point is our 1, 1 that we were given in the beginning. Our slope we just calculated as approximately 2, or it looks like it is 2. So we're going to use 2. Put these numbers in, and now you can get the equation of the tangent line, y equals 2x minus 1. And again, that would be the equation of the red line, the tangent line, that goes through that parabola at that point at 1, 1. Okay? So let's take a look at this concept of approaching. Here we have parabola. We could say it's the same one we just looked at if we want. We have the point here that it's approaching. They don't specify the point here, but if you want to say, for instance, it could be the point we just looked at, 1, 1, you can. If I pick 2 points on the parabola and draw a secant line. Now, a secant line, remember, is a line that goes through 2 points. So we have a secant line because it hits the graph here and here. And it would be bad if I didn't mention that the word tangent comes from the Latin word tangens, which means touching, because the tangent line just touches the graph at 1 point. Okay? The secant line cuts through the graph at 2 points. So we could use these 2 points to estimate a slope. Now, as we get closer to this point from the right, because we were coming from the right and we're getting closer. First we were here and now we're here. You can see that our line changes a little bit. And then if we get even closer, our line starts to get a little more like the line that we're looking for, T. So we can see this is what happens when we approach from the right. What about when we approach from the left? So approaching from the left, we're over here on this side, and we get this crazy secant line here. Not anywhere near close to this. So here's our secant line. So let's move it a little bit closer coming from the left. We'll put it here. Well, now at least we're starting to get a positive slope, whereas this over here was a negative slope, wasn't even close. But now we have a positive slope. So let's move it even a little closer. Here, again, now we're looking at something more similar to what we're trying to find, which is the slope of the tangent line. So you can see by this illustration, this is exactly what we did in the table. This was our table of values to get closer and closer and closer. This one coming from 2, so coming from the left, or coming from the right, sorry, coming from the right. And then this one coming from the left. Okay, and that's exactly what we did here in illustration. Okay, this is a big concept. That's why they took up that much room to show you each and every one of those. But getting closer and closer. If we were together in class right now, I would have you stand, I would pick somebody and have you stand looking at a wall, and I would ask you to take a step halfway to the wall. And once you did that, I would ask you to take a step halfway to the wall again. And once you did that, I'd ask you to do it again. And we would do that a series of times until you got really, really close to the wall. However, you're never actually going to touch the wall, but you're going to get so close to the wall that you might as well be touching the wall. And that's the concept that we're looking at here. Okay, let's move on to example 2. Example 2 talks about a camera, flash unit on a camera operating by storage charge on a capacitor, and it's releasing a sudden flash when it's set off. The data in the table describes the charge. So this is the data over here. Describes the charge Q remaining on the capacitor measured in microcoulombs at the time t measured in seconds after the flash goes off. So using the data to draw the graph of this function, we're going to estimate the slope of the tangent line, and they give us the point that they want us to take a look at. This is the slope of the tangent line at 0.04. Okay, so this time we don't have an equation. We just have a graph. And on that graph we have the points from the graph. And those points came from this table. And then we estimate that curve. So we had that big flash in the beginning, and then that flash starts to come down. Now, notice it's a negative slope. So when we are calculating our slope of the tangent line, we need a negative number. Now here are our points from the table. We have 0, 0.02, 0.04, etc. down to 0.1. And then here are our values. And again, we're looking right here at 0.4. All right? Now let's turn the page and see what we can do. All right, well, we need to pick 2 points so that we can estimate a slope, right? We only had 1 point. We had this point, which was 0.4, 67.03. And this comes from the table. So we want to pick another point. So if I take a look at the point, and I'm going to go back and forth here a minute, probably make you dizzy. But if I'm going to take a point, let's start with this one and put this point in. So we're going to take this point and find the slope. When I do that, I get negative 824.25. Now if I continue to do that with each one of these points, okay, so this is the second point. The first point is my 0.04 comma 64.03. So this is my first point, this is my second point, this is my slope. This is my first point, this is my second point, this is my slope. I just redo what I did before on all of these. Okay, now the point that I'm interested in is the 0, 4, 64, and 300ths. So I need to figure out how I'm going to estimate that. Well, these two are the closest to it right here. So I might want to take a look at those results. And I see that the result at 0.2 or 0.02 is negative 742. And at 0.6 is negative 607.5. So I think we can all agree that our answer would lie somewhere in between. So if we took the average of these two, because we do see that it's equidistant, then we could probably get pretty close to our answer. So we're going to use this method, and I'm going to take 742 minus 607 and 5/10. I'm going to take the average of that, which means add them together and divide by 2, and I get negative 674 and 7500ths. So we're going to estimate this by this method and say that our slope is negative 675. Okay, so that's another way you can find slope. Now, if I wanted the equation of that tangent line, which they don't ask for in this specific problem, but I could take the slope here, I could take my original point that they gave me here, which is the point in question, and I use my point slope formula again to get my equation of the tangent line. Okay, moving on to velocity. We have a velocity problem. So as you drive, if you all drive, you probably notice at the speedometer of a car as you travel in a city, and you see that the needle doesn't really stay still. Even if you have it on cruise control, there are things that cause it to come off a little bit. So the velocity of a car isn't constant. But we assume from watching the speedometer that the car has a definite velocity at each moment. So how instantaneous velocity how is instantaneous velocity defined? So instantaneous velocity is defined at a specific point in time. That's what we're going to look at. So here is example 3. The famous problem that everybody solves. Suppose that a ball is dropped from the upper observatory deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Okay, first we have to have a little bit of knowledge from physics. So we find out that in Galileo's law, he found that if you have this situation, he discovered that a distance falling freely is proportional to the square of the time it has been falling. So again, we're not taking into account whether there's wind that day, whether it's raining, whether anything else is causing that ball to fall at any different kind of rate. So the distance fallen after t seconds is denoted by S of t. And here's our equation. You probably noticed that that's familiar. Okay, so how are we going to find the velocity after 5 seconds when we're dealing with a single instance of time? Is the same problem that we had before when we had a single point. However, we can still approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second. So if we want to take a look at what the velocity might be at 5.1, that's pretty close to 5. So we're not going to pick something that's far away. We're going to pick something that's close. So here we have average velocity, change in position over time lapsed. That should look very familiar to you. It's the slope formula again. Okay? So notice here, I have my y values, s of 5 and s of 5.1. This is my y2 minus y1. My time lapsed is really just my difference between 5.1 and 5. So again, like I said, it is just like the slope formula. Okay, so I'm going to go ahead and put these values into my equation that I have. And when I do that, I will get 49.49 meters per second. Okay, so now that was just one example close to that number. We want to look at a few more than one. So if we come over here and we look at the time interval. Now here, this is a whole second apart, so that's probably pretty far away, but we'll put that in as our starting point. We have greater than or equal to 5 and less than or equal to 6. That was the average velocity of 53.9. This is the one that we just did, 49.49, or 49 and 49 hundredths. Now if I want to get even closer to 5, I want to lessen that distance. So this is 5.05, then 5.01, and then 5.001. And as I do this and I calculate my numbers, I see that I'm getting really close to 49. So at this point, I can estimate that my instantaneous velocity over the time when t is 5 gets closer and closer to 49 meters per second. I can summarize then that the velocity is 49 meters per second. Okay? If you have any questions about that, remember you can put it in the chat. Now, this is the graph. They're just showing here in figure 5 that this is really no different than what we did with the secant line before. We just looked at the amount of time getting closer and closer to the point. Same thing that we did before. And believe it or not, that is the end of section 2.1, which is tangent and velocity problems. So I think that's the shortest one we've done so far. So I will see you again for the lesson number 5 in day 2. Take care.